Good afternoon, everyone. I hope everyone is doing well. Um, and my name is Abbas, Jinia. I'm a third year PhD student at the University of Michigan. And today, our class will be on characterization methods. Before we get started, I just want to let everyone know that if you have any questions, please feel free to unmute yourself, pause me, and ask questions. You can also post your questions in the chat. I have the chat open, so I'm constantly monitoring the chat. And in today's class, we have some problems and some activities that we will be doing. So if you guys have your calculator around you, that will be very helpful. And, when we are doing this problems and questions, it'll be very nice if someone can volunteer and, unmute themselves and discuss the solution with everybody. Okay. Again, there's no pressure. It's okay if you want to put it in the chat, that's fine too. But I just want to make this class more interactive and let's just not be staring at the computer screens for an hour. Yes, so any questions before we get started? Perfect. So let's get started. So today's class, we're going to be covering the following topics. I know there was a class on gamma interactions and physics of neutrons, and we talked about some interactions. So we'll start with reviewing those basic interactions from our previous class. And then we will dig more into detectors and characterizing the detectors. So the first thing is when we have a detector, what kind of information do we get from the detector? So that was where we're going to be talking about the features of the gamma ray spectrum. The other two topics will be talking about efficiency and dead time. And then I'd like to introduce you to neutron time of flight. So this lecture, we're going to be covering two types of radiation. One would be gamma rays and the other will be neutrons. So let's get started with our review. So we have three major gamma ray interactions. One is photoelectric absorption. So what happens in photoelectric absorption that the incoming photon is absorbed, deposits all its energy to an electron, and then that electron is our desired signal when we are talking about detectors and detecting the radiation. Now, gamma rays, because they are uncharged particles, it's very difficult to detect them directly. So we want gamma ray to undergo some sort of secondary interaction in our detectors, and then they will result in some sort of charged particle, and that charged particle will be constituting our electrical signal. So in case of photoelectric absorption, it is the electron that will be responsible for that will give our desired electrical signal. The second interaction that happens, the second possible interaction that can happen in the detector is a Compton scattering. Now in Compton scattering, again, the photon comes in, but unlike the photoelectric absorption, the photon only transfer some portion of its energy. So in this case, we have two outgoing particles. One is a recoil electron, and the other one is the scattered photon. Now, the recoil electron will be the one that will constitute the electrical signal. Now, the scattered photon can again undergo a Compton scatter, and it can emit another recoil electron, and all these electrons will contribute to the signal. And the third type of interaction is a pair production. Now, pair production is not always possible. Now, for pre-production to happen, the energy of the incoming photon must exceed twice the rest mass energy of the electron. That's the minimum amount of energy that is required for this reaction to happen. Now, the rest mass energy of the electron is 511 keV, so we need about 1.02 MeV photon for pair production to happen. Now, in pair production, again, the photon deposits so whatever is the energy of the photon, 1.02 goes into the reaction, and then this particular reaction results in emission of an electron and positron pair. And again, these electron and positron are will contribute to our electrical signal. So these three interactions are mainly happening in any gamma detector. So whenever we talk about gamma detectors and we look at a spectrum, these are the three interactions that are happening in the detector. So let's talk about what kind of information do detectors give us. Now, we always see these sort of spectrum and we see these distributions, but what exactly do we get out of the spectrum when we are talking about radiation? So the very first information that we get out of the spectrum is how many radiation quanta are being detected. Now, of course, there is a radioactive source. This radioactive source is emitting radiation. But are we detecting all the radiation? Possibly not. Some of the radiation escapes the detector. But so we want to know how much of the radiation is being detected. So that's the very first information that we get. Now, some kind of detectors also give us energy information. So when we get an electrical signal, from that electrical signal, we can back calculate what was the energy that was deposited by the incoming radiation. Now, in this case, it will be gamma rays, um, and that's is very important. Energy information is very, very important in nuclear non-proliferation and safeguard applications because energy, with the energy information, one can construct the energy spectrum. Now we can think like that the energy spectrum is a fingerprint of a radioactive source. So if we talk about sodium-22, sodium-22 is a source that emit gamma rays and it also emit beta particles. And then that sodium-22 has a very distinct energy spectrum. And looking at the energy spectrum, we can clearly identify, okay, there is a sodium-22 source present. Now, sometimes if you have multiple sources present in, you have a sodium-22, cesium, cesium source, cobalt-60, etc., then again, the energy will, the presence of the energy line will tell us that, okay, this particular source is present in front of the detector. So that is very, very useful information. Now, this two important information, as I said, is visually represented in a spectrum. And the features of the spectrum will help us identify the radiation source. So let's talk about a general features of of gamma ray spectrum. So if you have a source, a very typical spectrum will look something like this, where we have a photopeak, we have a quantum continuum, then there is backscatter peak, annihilation peak, X-ray peak, etc. So these are general features. So if someone gives you a energy spectrum from a gamma rays, these features you are going to see. Now, what information do we get from this spectrum is what we're going to talk next. I'm going to pause for a minute here and see if there are any questions. Okay, since there are no questions at this point, I am gonna proceed.
Hey, Abbas,
Yes,
there is a question.
where? Oh, what about single and double escape peak? Yes, we will talk about double and single escape peak. So I will not answer this question right now, but it's coming up. Any other question? No? Okay. So first, let's talk about the photopeak. Now, how do we get a photopeak? So in order to get a photopeak, the incoming gamma ray has to deposit all of its energy. And out of the three interactions that we reviewed at the beginning of the class, we see that in photoelectric absorption, the photon energy is completely deposited in the detector. And the big contribution to photopeak is the photoelectric absorption reaction. Now, ideally, we want the incoming radiation to deposit all of its energy. Now, that's what we want, but sometimes it may not deposit all its energy. It will only deposit partial uh, it will only deposit partial energy. I see another question in the chat, but we are going to cover that as well. So the spectrum that I showed in the previous slide is a very, very basic spectrum, but we are going to be talking about every single feature that we see in the spectrum. So that will cover quantum continuum, pair production, single, double escape peak, everything. So yeah, ideally we want the gamma ray to deposit all of its energy, and photoelectric absorption is the best interaction. Now this brings me to talk about a feature of the detector. Now, there is something called as the resolution of the detector. What do we mean by resolution? So resolution actually is the ability of the detector to resolve two energy lines. For example, if you have two gamma rays, one emits a 1.1 MeV gamma ray, and the second one emits 1000 keV gamma ray. Now, these two energies are close to each other. So the question is, can we see two separate photopeaks in our detector? And this is something that is driven by the resolution of the detector. So the resolution will tell us if we will be able to separate these two energies in our spectrum. So how do we calculate the resolution? It's the full width half max of the photopeak as illustrated in the figure. And then we divide by the centroid of that photopeak. Now, if your x-axis is in units of energy, then the centroid of the photopeak is simply going to be the energy of the incoming gamma ray. Now, this can also be translated to the number of charge carriers that are produced in the detector. Now remember I said that gamma rays are uncharged particles, and if we want a desired electrical signal, they need to undergo some sort of interaction and produce some charged particles. And these charge carriers are basically the charged particles that are produced because of the three interactions. And the number of carriers produced is also going to drive the resolution. So we can use this formula on the slide to calculate the resolution of the photopeak. The second feature that we see is Compton continuum and edge. Now, as the name suggests, this is when an incoming gamma ray undergoes a Compton scatter process. So in this case, only partial energy is deposited by the gamma ray. So we have a scattered gamma ray and a recoil electron. And the energy that the recoil electron carries is what we see in our spectrum because that's the energy deposited by the incoming gamma ray. Now, there is a feature okay, so before we go into this Compton edge, let's talk about Compton continuum. How do we get this Compton continuum? Now, if you look at the very first equation, there is a scattered photon, and there is a term called cosine theta. Now, what is this cosine theta telling us is this cosine theta is basically the angle of scattering. Now, any angle is possible. So the photon can scatter in any direction, and therefore it can have a range of energy. So the recoil electron can have a range of energies, and that range of energy can lie anywhere in our spectrum from 0 to this Compton edge. And that's why we see a continuum. There is no distinct peak here, but it's a continuum. And this continuum is because of any scattering direction. Now, if you have a recoil and incident gamma ray are scattered at an angle of 180 degree, then that gives this feature of Compton edge. So when the scattered photon and the electron are back to back, are emitted, are scattered 180 degrees apart, then the electron is going to carry the energy. And when we take the difference between the energy of the incoming photon and the energy carried away by the electron, that will give us the position of our Compton edge. Or in other words, it's, sorry, not the, yes, the position of the Compton edge. Um, that will give us the position of our Compton edge. Next, we have the single and double escape peak. Now, this one comes from pair production. Now, pair production, what happens is the incoming photon deposits all it deposits its energy, and then we have an electron and positron pair. This also contributes to full energy deposition because the 1.02 MeV is, you can consider it as the binding energy of the reaction. So that much amount of energy is gone to produce the electron and positron pair. And the remaining, the excess energy, is distributed in the form of kinetic energy, and that is carried by the electron and positron pair. So when we look at the balance equation, the kinetic energies of the two particles, electron, positron, will be the energy of the incoming photon minus the twice rest mass energy of the electron. Now, positron is an antimatter and it's not a very stable particle. So what happens is this positron becomes, when the positron slows down, and when it is slow enough, it will annihilate, and the annihilation will result in emission of two 511 keV photons. Now, it turns out that the time that it takes for a positron to slow down and undergo annihilation reaction is very small. So for the detector, what happens is these annihilation radiation is emitted in coincidence with the original pair production reaction. So we can think like this: the pair production happens, and then almost instantaneously, we're going to have two 511 keV photons. Now, these are photons again. So these photons will deposit energy in the detector using one of the gamma interactions that we talked about. And these, if say these two photons, deposit partial energy, then they can be anywhere in the continuum. But say, for example, one of the photon escapes your detector, and then one 511 photon deposits all of its energy. Then in this case, what we see is a single escape peak. Well, as the name suggests, of the two 511 photons that are created, one escapes and this peak will be at an energy of h nu minus m naught c square. M naught c square is your rest mass energy of the electron. And if both the photon escapes the detector, then we see a double escape peak, and this will be at the h nu minus 2 m naught c square. So that will give rise to your single and double escape peak. Now we have some other features, annihilation and backscatter peak. So in the previous slide, we saw when pair production happens, there is a positron and positron annihilates. But what if there is a gamma ray isotope, there is a gamma ray source that consists of an isotope that decays by a positron emission? Again, now because it is decaying by a positron emission, annihilation will happen, and we will see a 511 peak in our gamma ray spectrum, and that's because of the annihilation reaction. Now, the other one is a backscatter peak. Now, where is this backscatter peak coming from? Now, let's think of this. We have a detector, and this detector is, it has to be protected from temperature, or, it has to be protected from the, you know, basically from it to get damaged. So you normally surround your detector with some material, and that is the surrounding materials. So we can think of it like this. So I'm going to use, so we have a detector crystal. We have a detector crystal. And this detector crystal is surrounded by some material. Yeah. A gamma ray comes in. Now this gamma ray first undergoes a Compton scatter reaction in the material that is surrounding your detector. So let's say the red one is the detector. Now uh, when it undergoes one Compton scatter, then the scattered photon comes in, and that scattered photon will deposit its energy in the detector. Now this one, so again, this reaction, theta has to be phi, because when the green photon comes in, your electron, your scattered photon needs to enter the detector volume. So your scattered photon enters the detector volume, and therefore your energy that the scattered photon is carrying will be given by the equation on the slide. And we do an approximation. So for the energy of the incoming photon much, much greater than 511 keV, it just reduces to 5, m naught c squared divided by 2 if we do the math. And therefore, the backscatter peak is at an energy of 0.25 MeV or less. Now, I want to ask a question to the class. Will the backscatter peak have, so the resolution of the backscatter peak, will it be better than the photopeak, or will it be poor than the photopeak? Take a moment, think about it, and then someone can unmute, or at the count of 3, you can post the answer to the chat. So again, my question is, we have seen a backscatter peak in our spectrum, and will this backscatter peak have a better resolution than the photopeak, or will it be worse? So let's take a minute to think about this. Okay, I'm seeing a lot of people saying it's going to have a worse resolution. Nah, okay, great. So yes, the correct answer is worse resolution. Now, let's try to, so my next question is, why will the backscatter peak have worse resolution than the photo peak? That's correct, Raymond. Worse due to Compton distribution. Now remember, these gamma rays can undergo any of the three reactions that we talked about. So if the scattered photon, the scattered gamma ray, where once it enters the detector and it undergoes Compton absorption, that's the ideal case. But Compton absorption there is a probability that a given gamma ray, given gamma ray will undergo Compton absorption. And this probability is a function of energy and the detector material. So most likely, majority of the times what happens is the scattered photon will undergo Compton scatter. And as we said, in Compton scatter, the electron, recoil electron, can have any energy, and that will affect the resolution of your backscatter peak. And therefore, it will have a worse resolution than the photo peak. Now, Compton scatter, another thing that I want to point out, Compton scatter can also contribute to your full energy deposition. And how that can happen is a photon comes in, it undergoes multiple Compton scatter, and after going multiple Compton scatter, the energy of the photon is so low that it will finally be observed, it will finally be captured by photoelectric absorption in the detector volume. And that will give us to full energy deposition of the incoming photon. But the question is, will this contribute to the photo peak? Well, the answer to the question is yes, it will not. It will not contribute to your photo peak. It's a full energy deposition, but it will not necessarily contribute to your photo peak. And the reason is, how fast is your detector in collecting the electrical signal? So you say, for example, we had one Compton scatter, and that Compton scatter gave us one signal. Now, is your detector fast enough to collect all that signal before the second Compton scattered electron constitute an electrical signal? Depends from detector to detector. So the general answer is going to be no. It will not contribute to your photo peak, but it can still have a full energy deposition in the detector. All right, guys, question one. So what we are going to do is, I have a spectrum. This is a sodium 24 spectrum recorded using a 2-inch by 2-inch sodium iodide crystal. There are two questions asked in this, and we are going to try to answer the question. So first one is identify peaks 1, 2, 3, 4 in the spectrum. This is covering all the topics that we talked about until now. And then a B part is a sum photo peak. So let's take, say, 3 minutes, and then we try to work out this problem, and then we'll talk about the solutions. So 3 minutes. Just a request, so we'll wait for 3 minutes before we post our answers to the chat, or we say it out to the cloud. Okay, so you guys want to post your answers to the chat, or if anyone wants to say it out aloud, just feel free to unmute yourself.
Yeah, I just want to try, although I'm not sure.
Go for it.
Like, yeah, the number 4, I think it will be a single peak for 2754. And then
Mm-hmm.
3 will be, I think, a double peak for that same gamma.
Mm-hmm.
Well, if we move to number 2 and number 2, I think it should still be the single peak, but for the 1369 gamma, and then the 1 is for the double. Although I'm not so sure, or 1 can be due to backscatter.
Right. Okay. So number 1 is backscatter peak. If we look at the energy, it's roughly at m naught c squared divided by 2. M naught c squared is 511, rest mass energy of the electron. So if we see, a peak around there, most likely it is from a backscatter peak. Number 2. Now, number 2 is not exactly a single escape peak from 1369. Now, if you look at the energy, it's a 511 keV. Uh, when if we go back, 2754 and 1369, they both exceed 1.02 MeV. So they both can undergo pair production. And where pair production happens, we have a positron. Whenever there is a positron, you will likely see a 511 peak from the annihilation process. So pair production resulting in positron emission, and that giving the annihilation peak 511. And 3 and 4 was correct, single escape and double escape peak from 2754. What about part B? That is absolutely correct. So some peak basically means if both the photopeak deposits all of the energy in the detector at the same time. Now, again, this one is very, very less probable, but it can happen. Both the energies depositing all of its energy at the same time in the detector. And that's where the backwards on 3 and 4. Raymond, I don't quite follow your question. So do you mind explaining what you mean by that?
Abbas, I think what they're saying is that the single escape peak is labeled now at 3, the lower energy, and the double escape peak is the one at 4.
Okay, sorry. Yes, that's a very good catch. I apologize for that typo. So yes, 4 is single escape and 3 is double escape peak. Good catch. Thank you very much. Yeah, so let's move on to the next topic, and that is the efficiency of the detector. Now, efficiency, when we talk about efficiency, we want to see how much of the radiation are we able to detect. Now, if we have a heavy charged particle, such as alpha or beta particles, these heavy charged particles don't travel, very far. So once they enter your detector, the detector will be able to stop these heavy charged particles and they will be detected. So the efficiency in this case is 100%. But for uncharged radiation, like gamma and neutrons, um, first they undergo secondary interactions, one, and when they undergo secondary interactions, no, it's not quite sure that how much energy they're going to deposit. And then also they can travel very large distances between the two interactions. Like for example, gamma ray, if it is undergoing a Compton scatter, between two Compton scatter, they can travel large distances. So here the efficiency takes a hit and we will have efficiency less than 100%. So how do we calculate the efficiency of the detector? So not very fancy. We take a detector and just measure it. If we know the source strength, that is how many radiation quanta are emitted by the source, say that's S, and then we have a detector, sodium iodide detector, and then we just look at our detection rate, just count the number of electrical signals we got in the detector. And when we take the ratio of that, that tells us the absolute efficiency of a particular detector. There is a second term in efficiency that we normally refer to is the intrinsic efficiency. And what is the intrinsic efficiency? Now, when you have a radioactive source, now not all radiation will be emitted in one particular direction. So, most of the times our commonly used radiation sources like sodium-22, cesium, or a californium spontaneous fission source, radiation is emitted in all directions. So if we want to get a better understanding of how much we are detecting, we have this term of the radiation quanta incident on the detector. So that means if we have 1,000 radiation quanta incident on the detector and we detect 999 of 1,000, then that's a great detector because pretty much all the radiation that was incident on the detector was detected. And intrinsic efficiency is a more informative about the efficiency of the detector. And again, these two terms, these two efficiencies are related by something called as a solid angle. So solid angle is, we can think of how much surface area, so how much area, detector area is being seen by the source. So that gives us an idea of how much radiation will be incident on the detector. And I have another question for you. So this one is on efficiency. So again, we have a sodium iodide detector. There's a cesium-137 source. And this the detector and source are separated by 1 meter. And I want to calculate the absolute and intrinsic efficiency of this detector. Now this one is a little bit tricky, so I want everyone to think about this and then we will go on. So how about we take again, let's say 3 minutes. All right. So anyone wants to volunteer and give it a shot? Just feel free to unmute. All right. So, okay, let's see how we will go about it. So first of all, let's calculate our absolute efficiency. Once we know the absolute efficiency, then we can get to the intrinsic efficiency. So for absolute efficiency, we require two things. One is uh, detection, how many electrical signals were detected. In this case, 10 to the 3 detection signals per second. And the second term we need is the number of gamma rays emitted by the source. Now, this source does not always emit gamma ray. So if we look, excuse me, if we look at the decay scheme, 95% of the times it decays by beta minus. And then when it decays by beta minus, it is 85% probable that it will emit a gamma ray, which is 662 keV. And since sodium iodide is a gamma ray detector, we will be seeing the 662 keV gamma rays from the cesium-137 source. So if I want to calculate the number of radiation quanta emitted, I will take the activity of the source, which is 1 millicurie, convert that to disintegrations per second. So that's where we have the 3.7 times 10 to the 10. It's converting curie to becquerel, and 1 becquerel is 1 disintegration per second. And every time it disintegrates, 85% is the probability that it will emit a 662 keV. So then when we simply take the ratio, we get our absolute efficiency. And using this absolute efficiency and the solid angle, we can get our intrinsic efficiency. So what we see here is that your intrinsic efficiency is slightly higher than, is twice your absolute efficiency. Does this make sense? Is it like, can you have a higher intrinsic efficiency than your absolute efficiency? What do you guys think? Yes, someone is talking.
Do you have an error in your formula at the bottom for the solid angle? D would be 100 centimeter rather than a hundredth of a centimeter.
Oh, that's right. So we should have, it's 1 meters and not centimeters. Correct. Thank you. All right, I am going to fix the slides before they are sent out. All right, the next topic that we have is the dead time. Now, again, what is dead time? It is the minimum amount of time that is required to separate two events so that they can be detected as two separate electrical signals. So we have these three terms in the that we need to account for. Is one is your true interaction rate, then what is your recorded count rate, and then your detector dead time. Now, recorded count rate, so your true interaction rate is going to be higher than your recorded count rate because your detector will take some amount of time to collect all the charges or all the electrons that are produced by the gamma ray, converted into an electrical signal. And when it is doing that process, if another interaction or if another radiation, if a second radiation quanta comes in and deposits its energy, the detector will not be able to process that. So it's dead essentially for that amount of time. And this is what is the dead time of the detector. Now, for dead time, calculations are important if you want to estimate the number of radiation quanta that is emitted by the radioactive source. Now, this is again very important in nuclear non-proliferation applications because we want to know what is the source strength. Even from licensing point of view, we need to we need to know what the source strength of a particular radioactive source is. So there is an experimental way how we can estimate the dead time of our system. And this is called a two-source method. Two-source method is commonly used to estimate the detector dead time. So what we do is we take one source, put it in front of the detector, and just see what the detected count rate is. Now, and then we take a second source, again, repeat the same process. And in third time, we have both the sources being recorded simultaneously. So we have N12, meaning source 1 and source 2, both are in front of the detector. And then there is one source and then the second source. Now, all these sources will have some amount of background radiation. So the total count rate that we get from the detector is the sum of the radiation emitted plus some background radiation. So in this case, when we do the math, so we have N12, when both the sources are being measured together, that will include your background radiation, will be the sum of the two count rates, N1, N2. But again, N1 and N2 have to be corrected for your background radiation because when we measured N1 alone, there was some background radiation present. And what we see here is for a non-parallelizable model, when you work out the math and you solve for tau, we can determine the dead time of our detector. Now, this is a very easy experiment. All we need to do is just have two sources and measure them with our detector, and that's how we can calculate the dead time of the detector. So this marks the end of our gamma part. So does anyone have any questions? What is a non-parallelizable model? So when we are talking about dead time estimations, there are two models called as parallelizable and non-parallelizable model to account for dead time of a detector. So let me do this. Okay, is this working? All right. So we have time here and a radiation comes in. Okay, so this one is a radiation. So only one radiation came in and we have this whole radiation was detected. But now a second radiation comes in. But before this was completely processed, there was another radiation that came in. Now, this two radiation will be detected as one radiation because it arrived within the delta T. And these non-parallelizable and parallelizable models are two different ways of accounting for your arrival of two radiations within your tau period. Now, sometimes what will happen is in one of the models, what it will do is it will just simply ignore the second radiation. What it will do is, so if these two radiation comes in, the detector will have one signal, and then it will be completely blind to the second radiation. And then when, once it has finished processing this, that's when it will take into account the second radiation. So these are just the ways of, these two models are, we can think of it as theoretical models of accounting for dead time corrections, so that we can relate the true interaction rate and the count rate of the detector. Any other question? All right, so since we are almost at 2 p.m., I'm going to briefly talk about neutron time of flight. So neutron time of flight is used to characterize neutron detector. Now, this one is a very, very powerful experiment because it not only helps us to characterize neutron detectors, but it also helps us to construct the energy spectrum of a neutron source. Now, in this case, scatter-based detectors are normally used because these detectors are sensitive to fast neutrons and they provide energy information. So when a neutron scatters in a scintillating detector, the pulse, the output electrical signal, is proportional to the energy deposited by the incoming neutron. Capture-based neutron detectors, such as traditional helium-3 detectors, are not favorable for time of flight. And again, the reason for is one, they are sensitive to thermal neutrons. And when fission happens, neutrons emitted are all fast neutrons, so they are highly energetic. And there is no energy information. So every time when a neutron is captured in a helium-3 detector, what we get is a transistor logic signal. Whether it's a yes, that means a neutron detected, or a no, no neutron detected. So we can't exactly get any energy information in capture-based neutron detectors. So what's the principle of your neutron time of flight? So we use two detectors, detector 1 and detector 2. The source that is being investigated is close to one of the detectors, and that is your start detector. And you have another detector which is your stop detector. So what happens is fission is basically a correlated event. So when a fission happens, multiple particles are emitted per fission. So one particle will go in detector 1 and it will start the clock. And then the second particle will go in detector 2 and that will stop your clock. When you take the difference between the two, using that time, we can actually calculate the energy of the incoming particle in the stop detector. The reason why we can do that is because the flight path between start and stop detector is fixed. We know that flight path. So a typical time of flight spectrum measured from a Californium spontaneous fission source will look something like this, where all the gamma rays, because gammas, regardless of their energy, always travel with the speed of light, so they will arrive at the exact same time. And then neutrons, because their energy, their arrival time is dependent on the kinetic energy of the incoming neutron, you're going to have a wide neutron distribution. And this wide neutron distribution is because of different kinetic energies of the neutrons. Now, using this spectrum, using this time of flight, we can actually construct the energy spectrum using this equation. So the energy, kinetic energy of the neutron will be given by half mv square, and velocity is your distance divided by time. We know the time we get from our experiment measurement, and d is a fixed distance. Now, these are three parameters that determine the accuracy of your energy spectrum. So one is your source to detector distance, how accurately we know the distance, the detector depth. Now, the reason why we are talking about detector depth is there is a hidden assumption here, and the assumption is that uh, in our start detector, your start detector, every time a fission happens, the radiation will interact instantaneously. Now, there could be some travel time, but we are neglecting that. And that's why we say the depth of the detector. And finally, how your bin size. So when we histogram all our time differences, what is our time bin size? So coming to the character, I'm going to skip this question because we don't have time here. So we're coming to the neutron detector response. So how can we actually get the detector response from our time of flight measurement? And this is what we can do is, first of all, unlike electrons in a scintillator detectors, neutrons response is not linear. So neutrons, when they undergo secondary interaction within the detector, the energy and the light that is created in your scintillating detector are not linear, unlike electrons. So because they are not linear, we need to have a response function. So how much energy, when we have a 1 MeV energy, what will be the amount of light produced when it deposits all of the energy in the detector? So if we carefully look at the time of flight spectrum here, we have two pieces of information. Using the time difference, we can calculate the original energy of the incoming neutron. Kinetic energy is half mv squared. And then, as I said, scintillator's voltage pulse is also gives you energy information. So the 1 MeV neutron, when it arrives at your detector, it is not always going to deposit all of its energy in the detector. It can deposit any energy between 0 to 1 MeV. So using the pulse height or the pulse integral, using that signal, we can estimate how much energy was deposited in the detector. So here what we get is energy deposited, and then we have the original energy of the incoming neutron, and that's how we can construct the detector response function. Now, this detector response function is again very important because if we have an unknown source, this response function will actually help us to unfold a energy spectrum. So with that, I will take any final questions. Gamma, how can you know okay, I see a question. How can you know the gamma is from a fission event and not from other reactions? Yes.
No, hold on for the spade.
Sorry, is that a question?
I'm a Zellari.
Okay, can you know that the gamma is from a fission event, not from other reaction? Yes, that's a very good question. Now, it's not straightforward to know that the given gamma is from a fission event and not from other reaction. Now, normally the purpose of time of flight is, we are mainly interested in neutrons. So what will happen if you have two detectors, detector 1 and detector 2, okay? And the gamma that we collect, okay, so fission happened, a neutron went in this detector and a gamma came in this detector. Now, if this were from the same fission event, then the time difference between the two cannot be greater than your, say, for example, if what we can do is we can set up a coincidence time. We can set up an interval between the two detectors. So meaning if your delta T exceeds a certain number, say, if it exceeds T max, then you know that these two particles are not correlated. Now, the question that we can ask is, how do I get T max? Now, T max can be calculated using the energy of your slowest neutron, because slowest neutron is going to take maximum time to travel this flight path. Fast neutrons are going to be very instantaneous, but your slow neutrons will take much longer to travel the flight path. So this T max we can calculate using the energy of the slowest neutron. And if anything, if the time difference exceeds that T max, then we know that this is not a correlated event, or it's coming from other interaction within the source, or a background gamma just happened to interact. Okay, let's see the next question. When we collect the electrons from the detector, okay, so we have different particles. How do I identify them with time of flight method? Again, all these particles, they are gonna have different travel times. And because the masses are different, so their travel times are gonna be different. So we can take the time tags and determine if it is coming from a neutron or something else. The other thing is normally the type of scintillating detectors that you use in your time of flight setup, you want to make sure that those detectors are sensitive to the particle that you are trying to characterize. So if you're trying to detect neutron, then you want to use a scintillating detector that is going to be sensitive to neutrons. For alpha particles, you would want to use an alpha scintillator, etc. Now, there is a question on electrons detector. How are the remaining positively charged ions affecting my signal? Now, in this case, it really goes into how your detectors are made. Now, there are certain types of detectors. These are gaseous detectors. And in these gaseous detectors, your charged particles, heavy charged particles, and your electrons, they are ionizing your gas every time it is. And that ionization is actually what is constituting your electric signal. So it really depends on from detector to detector type, and then what type of electronics are we using to collect the signal.